Bueno, you're going to speak in English,
Yes.
so I'll just give the introduction in English as well. Welcome everyone to the seminar in Applied Math from the Universidad Católica. Our speaker today is Anastasios, a professor here in the Institute for Mathematics and Computational Engineering. He obtained his PhD in Scotland, right?
That's correct, yeah.
And
100 years ago.
yes. He's been around the world and spent a lot of his academic career in the United States, at Brown University and in other universities, and with some sabbaticals at Oxford and UH. He works in stochastic partial differential equations, among other related topics. And yeah. So let's welcome him with an applause.
All right, thank you, Federico. Is that yours?
Yes, sorry.
Yeah, fine. All right, so first of all, thank you for being here. This is work that I did with Maria Ptasnik some years ago. It's a relatively old work, but I decided to revisit it because I have some new results. And I thought I should, kind of refamiliarize myself with the techniques in that paper we published. And what better way to do so by giving a talk or a couple of talks, right? So that is the purpose of this talk. All right, so that's about stochastic homogenization. This is not about stochastic PDEs. All right, so I will start by telling you a little bit about what chemotaxis is. All right, so chemotaxis is essentially a process of stochastic gradient ascent that is implemented by eukaryotic and prokaryotic cells by various cell types. So the idea here is that if you have a cell that moves around and it detects a nutrient, all right, eukaryotic cells, for example, has receptors that can use to compute the gradient of the concentration of that nutrient, and usually they tend to move randomly up the gradient of that nutrient, right? They want to find more food, more sugars, for example, right? And similarly, if there is something toxic in the environment, they want to avoid it, so they perform some sort of a stochastic gradient descent. Okay. Now this is also employed. This is also used for cell communication. If a cell, let's say a immune cell, lymphocyte in your body detects a viral infected cell, it's going to initiate a program. It's going to kill that cell, but presumably there are other viral infected cells in the region. So basically, it will call its friends, right? It will secrete some sort of a chemical signal, and then other cells will move up the gradient of that signal. All right. So it's some sort of a biological implementation of an optimization algorithm in some sense. And the first people that wrote down equations for that, this is the famous Keller-Siegel model. Keller and Siegel wrote this system of PDEs in the 70s. And the first equation is, U here is the concentration of some type of cells that move chemotactically towards a chemoattractant up a gradient. So you see it's in conservation form, and basically what you have here, you have some randomness, right? You have the Laplacian here. And then here, basically, you have some convective movement up the gradient of the chemoattractant. So V is the chemoattractant. Okay. And of course, because here you have fluxes, all right, so the flux is going to be proportional to the number, the density, let's say, of cells. So that's why you have this non-linearity over here, U gradient thing. Right? Now, you can have different mechanisms. Now, that's the important equation, the first one. The second one implements or represents the mechanism by which these chemoattractants are secreted, are produced. And for the system that Keller and Siegel were looking at, they were looking at a specific cell type called dictyostelium. So these cells constantly produce a chemoattractant, all right, in a specific phase. So basically, dictyostelium is a fascinating organism, which basically can transition between unitary cells, which can fuse and form a multicellular organism. And so basically, they are unitary cells, they move around. When they don't find sugars, food, or whatever, they start secreting this chemoattractant. And if you have a colony over here, they're going to start fusing. They're going to start secreting more chemoattractant. And cells in the periphery, they're going to start getting attracted to the organization center, right? Okay, so what you have here is basically constant production proportional to the cells, some sort of decay because the chemoattractant in tissue kind of decays. All right, and you have the diffusion. All right, so this system fascinated mathematicians for quite a while. So I have some more references here. There, yeah.
So P sub U and P sub P are just the makers.
Right, it's a tensor, yeah. I'm gonna focus on the one-dimensional system for a while, then I'm gonna go to one-dimensional system, right? Okay, so these systems kind of fascinated mathematicians for quite a while because it was known that, you know, sometimes they can blow up. Of course, you have to put boundary conditions and initial conditions and so forth. I'm gonna start doing that gradually. But imagine for the moment that you're in a bounded domain, you have zero flux boundary conditions, some initial conditions with some regularity. The regularity is important, we're going to discuss it. But the idea is that very early on, mathematicians observed that this system can blow up in finite time. And you know, there was a bunch of papers in the early 2000s trying to pin down the conditions under which this system has global in time solutions and under which it blows up in finite time. So in one dimension, given some mild regularity in the initial conditions, this system has global in time solutions, right? But as soon as you go into dimensions 2, 3, and so forth, the question of whether the system is going to blow up in finite time depends on the initial conditions. So it depends specifically on the L d over 2 norm of the initial conditions, d being the dimension of the system. All right, there is a threshold, and above the threshold, the system blows up. If you're below this threshold, then the system has global solutions in time. All right, so
there's well-posedness in one.
There's well-posedness in 2D and 3D, but depending on the initial conditions.
Right. But in 1D, it's in general.
In 1D in general.
And then.
Yeah. Okay. All right. So, and that's the reason why today I will be talking about some results in 1D, but in the paper we have also investigated 2D and 3D, but I want to basically present, you know, the story in its simplest form. All right. All right. So what Maria and I were interested in the situation where basically these motility parameters, like the diffusion tensor, or like the chemotaxis, this chemotaxis coefficient, and so forth, are random. They're random variables. They have a dependence on omega. So this is going to be a measurable dependence on some probability space. So these are going to be random fields, and I'm going to start defining notions. And the reason for that is that it is very well known that in biological tissues you have all these proteins embedded into the tissues, all right, that affect the motility parameters of the cells. And these proteins are macromolecules. So basically they form structures at a completely different scale at the nanometer level versus the micrometer level where the cells live. All right. Hence this division over here by epsilon. All right. So there are two scales inherent in that problem. Now the chemical, the chemoattractant, is not affected by these proteins, right? Because it does live in the nanoscale level, but the cells will be affected by structures, and the motility parameters will be affected by structures at the nanoscale level. All right. And so as we move on, I'm going to start making some assumptions, which, you know, this is an introductory slide, but as we move on, I will tell you that we're going to assume that these coefficients are ergodic random fields. All right. And there is another like probability space. So the main question that we want to address, and I want to visualize it for a moment with a periodic configuration. So imagine that these matrices over here, these tensors, are you know, periodic in the domain. All right. So basically, imagine that you have this configuration over here, and the motility parameters over here take a different value over the black dots and a different value over the gray matter. All right. What this x over epsilon does, of course, is that as epsilon goes to 0, you zoom out, and so you start having a separation of scales. All right. And so homogenization is this area in PDEs where you ask the question, all right, so I don't want to deal with this microscale over here. As epsilon goes to 0, can I prove that the solutions, and again, I don't have boundary conditions here, you know, I'm going to start, putting more details here, but could it be the case that the solutions to this system with appropriate boundary initial conditions converge to something, and what kind of PD that something would satisfy presumably it will be a PDE with constant coefficients, a homogenized version where the material doesn't have any microstructure anymore. And if this is the case, we can deal with that PDE, all right, and we don't have to devise elaborate numerical methods to deal with the microstructure here. And periodic coefficients appear very frequently in homogenization theory because it's the simple fact of life that if you have a periodic function over some bounded domain, if you have that periodic function with argument x over epsilon, as epsilon goes to 0, that weakly converges to the average of the function over the period. All right, so you have some convergence here if these guys are periodic. All right, yeah.
I have a question. When you say random.
Yeah, I'm going to elaborate. Okay, I'm going to start defining things.
Okay.
Right? That's an introductory slide. Right?
Okay.
This is someone just waving hands.
Fair enough.
All right. Now, Maria and I, we were not interested in this kind of periodic configurations. All right. So we were interested in situations. So imagine if you want to visualize here now that these dots are not periodically arranged, but they could be given by a Poisson random field. The centers of these circles could be a Poisson random field, so they could be distributed randomly. All right. So in that kind of situation, you don't necessarily have some sort of convergence when you scale, so you have to do something special. All right. And so you will have some measurable dependence on all of these functions on another line probability space that I'm going to define. Yeah, go ahead.
Just maybe you mentioned it, but are you assuming some sort of regularity in this periodic function?
Yeah, so of course you have to, you have to impose regularity. As I start proving things, I will have to impose regularity conditions and everything, right? So this is just so the theorem that I'm going to start building towards to, all right, is going to be this guy. All right, so under some assumptions on ergodicity and certain regularity conditions here on the second derivatives of this tensor and so forth, we're going to prove existence of solutions for this problem. Okay, I'm going to define what a solution means given the stochasticity, of these coefficients. And basically, as epsilon goes to 0, we're going to prove that, again, here I have adopted, this is the one-dimensional problem, I have adopted Neumann, zero-Neumann boundary conditions, certain initial conditions which will have a certain regularity, we're going to see. And basically, the solutions of the system with the microscale will converge in some space and almost surely with respect to the underlying probability space to a system with constant coefficients. All right, D star and X star. Notice that here I didn't have any dependence on epsilon. So this depends only on the microscale, right? Because that's a chemical. Okay. All right. And this will involve, you see here, I have these spaces L2 potential of omega. So here I'm going to standardize a little bit notation. In whatever I talk about, Q is going to be the geometric domain over which the PD is set, and omega is going to be the probability space. So you see immediately that since I'm talking about gradients over the probability space here, there's going to be some sort of a stochastic derivative. I don't have Euclidean structure over the probability space. All right. Okay, so let's start building. Before I talk about stochastic homogenization, I hope you understand what the main result is, right? So we want to avoid, we want to asymptotically get rid of the microstructure, and hopefully if there is a big separation of scales in the problem, then since we have the limit, we can approximate the solution of the problem with the microscale by solving a PD that doesn't have the microstructure and it's easier to kind of attack numerically. All right. Before we talk about stochastic homogenization, I have to tell you a couple of things about periodic homogenization so that we can understand the stochastic homogenization. In periodic homogenization, you always get products of weakly convergent sequences, right? The prototypical example would be something like, your Poisson equation, right? So if you have minus divergence of some coefficient x over epsilon, right, even in 1D, right? Gradient of u, all right, is equal to f. My handwriting is dreadful, I apologize about that. You can put in some domain q, all right, and you can put, u is equal to 0 on the boundary of q. Okay, and so the idea here is that, you have a priori estimates, you can use Poincaré inequality, okay, you can say that the solution is going to be bounded by a constant times the L2 norm of f, if f is in L2, all right. You know that you will have a convergent subsequence, all right, for this gradient over there, and you know that this weakly, and you know that this will weakly converge to something, but you have a product of weakly convergent sequences, which doesn't have to be weakly convergent. And so what people do sometimes formally, this is not rigorous mathematics, but in order to derive the equation at the limit, all right, they assume that the solution has an asymptotic expansion of the form. So they assume that, so I should say that this is u epsilon, let's say, and I have u epsilon right here. They assume that u epsilon of x is some u naught of x that doesn't depend on microstructure and a perturbation that reflects the microstructure plus epsilon of u1 x over epsilon, right, plus epsilon squared u of x u2 x over epsilon, all right, and it goes forth. And basically what people do, and again, this is completely formal, they substitute this in the PDE. If the PDE is linear, then they isolate powers of epsilon squared, so they isolate powers of epsilon, and they derive some PDEs. Now, that's completely formal. You don't know that any solution here have the Poisson equation, but you don't know if any solution will have an asymptotic expansion. You don't know if your PD will have any solution at all. So, garbage in, garbage out, right? So you can apply this, but it doesn't really do anything. All right, so you have to deal with these products of weakly convergent sequences, and there are a lot of methods for doing so. One of the most well-known is compensating compactness. Another one is this scale of two, this notion of two-scale convergence by Allaire, which was introduced by Allaire, okay, which I want to describe to you right now. All right. So this sits somewhere between weak convergence and strong convergence. So the idea is that you have a sequence of functions. All right. These could be solutions. All right, with that diffusion tensor over there that depends on x over epsilon. Now, two important things. The test functions here have a periodic component which is scaled according to epsilon. So the test functions are functions from the geometric domain to periodic functions over the period. Okay, smooth enough. And you will see why this is important in just a minute. And since you have a periodic component, at the limit, you're going to get the average over the period, okay, of this expression. Okay, you know xy, all right, phi xy. Right, that's a definition. All right, but this definition embeds this knowledge that we have that periodic functions periodic functions applied to x over epsilon will converge weakly to the average over the period. Now, there are a couple of compactness arguments that come with that kind of convergence. If u epsilon is bounded in L2, then you have a convergence subsequence, convergence in this notion of two-scale convergence. All right, you have the two scales here, all right, in the test function. Okay, but of course you have, because you have extra structure, you have more compactness theorems. You have, for example, this guy, which is very consistent with that asymptotic expansion over there. It says that if u epsilon is bounded in H1, then okay, u epsilon will converge in the two-scale sense to some u naught of x, all right? But the gradient of u epsilon will converge to the gradient of u naught of x plus the gradient with respect to the periodic component of u1. And that's kind of consistent with this guy, right? Yeah, because if you take the derivative over here with respect to x, you will have an epsilon, but if you take the derivative with respect to y, the epsilons will cancel out. And so you're going to end up with the derivative of this guy plus the derivative with respect to y of u1, and everything else will cancel out. So, this is a mathematical theorem, all right? That over there is just a formal treatment, but it captures the structure, the compactness result captures the structure of the formal treatment. There are generalizations of that. What happens if the derivative, the gradient is not bounded? Well, if the gradient is not bounded, but epsilon times the gradient is bounded, you can get again some sort of compactness results. Okay, that generalizes the previous one. All right, so this is just an introduction to periodic homogenization. So what good is that? All right, so let's see how this works, why we define that. All right, so again, imagine the Poisson problem. So here I have it in a slightly more general situation than there. All right, there, the diffusion tensor is periodic. Here I have a periodic component. So this A, in one dimension, this A x y could be of the form x plus sine of y. And then y, I said x over epsilon. So it's not a periodic function, but it has a periodic component. All right, if this didn't have any dependence on x, by homogenizing, I would like to get here a constant. Here, by homogenizing, I want to get something that gets rid of the microstructure. So I don't have to numerically deal with the microstructure. How do you do that? Well, again, you know that by a priori estimates, you know if f is in L2, you know that the H1 0 norm of u is going to be less or equal than the L2 norm of f. You know it's bounded. So basically, you have the compactness result modulo a subsequence that I was just mentioning with this extra structure over here. All right. And so you set up this in weak form. All right. You set up this equation in weak form with a test function which is of this form over here. That's not periodic, but it has a periodic component consistent with the definitions that we have. And if you were doing everything that I'm doing up to here with weak convergence, here you would be stuck, right? Because you would have basically the gradient converging weakly, this guy over here, the periodic component converging weakly, but the product of weakly convergent sequence wouldn't be weakly convergent. You can employ something like the div-Kerr lemma, compensated compactness, but the genius of this definition is that it says, look, the test function depends on epsilon, so we're going to pass this to the test function, all right? So we're going to use this as a test function, and we know that the gradient of u epsilon two-scale convergence, it has the two-scale convergence, that's what I'm trying to say, all right? And we get a limit, all right? Of course, the limit has the average over the period, right? Because that's how two-scale convergence works. And now we have two test functions over here, and this is a macroscopic equation. I mean, we don't have any epsilon anymore, but we don't like this u1, so we can get rid of this guy. All right, so we proceed in two steps. If you set the test function phi equal to 0, then here we have the gradient with respect to y. I do integration by parts, and I'm going to get the divergence of this expression with respect to y is equal to 0. So this will tell me that I can express, if I do that in detail, this will tell me that I express u1 as a linear combination of the elements of the gradient of u, where these weights over here satisfy what is called the unit cell problem. This is derived by this variation form if I set phi is equal to 0. It's not an ansatz, it's a theory. And now if I get this and I plug it up here, and now I set phi 1 is equal to 0, I will get the divergence outside the integral here with respect to x. All right. And of course, the gradient of u of x is going to survive here. So I'm going to have it here, and I'm going to have it in this expression. So I'm going to have this member of the basis here, and the gradient with respect to y of these weights over here, and I get the homogenized diffusion tensor. All right. So I get convergence to a homogenized equation. I don't have the microscopic structure anymore. If initially I didn't have any dependence on x, here I would be getting a constant. Oops, here I would have a constant. But now I have a dependence only on the macroscopic variable. So this is great, right? This is really nice, because now we don't have to have any specialized numerical method for the microstructure, and we know that the solutions of the microstructure converges to the solution of the homogenized problem. All right, and I took too much time on that, so I apologize about this. But the idea is that this is great. There are something like 4 or 5 methods for dealing with this, especially if you focus on the Poisson equation as a prototypical problem, you know, compensated compactness, div-Kerr lemma, something called, you can use gamma convergence methods here, but this is very flexible, this two-scale convergence. All right, the problem is that you have to assume periodicity. And, you know, this is not what we're interested in, Maria. People use that in various problems in material science with crystals, with periodic configurations, etc. But we were interested about stochastic gradient ascent, where the motility parameters are affected by a random distribution of proteins in the tissue. All right. So, yeah.
You mentioned gamma convergence.
Yeah.
So I didn't understand. So you can't use gamma convergence?
You can use gamma convergence.
You can use it.
Homogenization, yeah. Of course, you have to have a variational form, and you have to, you know, because you care about the minimum, etc., and so forth. Right? There are all sorts of convergences that there's something called age convergence that you can use. There are a lot of techniques that basically they're designed. A number of them, probably you have seen the div-Kerr lemma, right, in fluid mechanics, right? So that deals exactly with that, with products of weakly convergent sequences. Right?
Boundary condition doesn't play any role.
Of course. Here the boundary conditions, of course, yeah. I mean, here the boundary conditions were de-Rislett, but in the problem that I'm going to focus
Yeah,
on.
that's okay, but what changes? What changes?
Well, the weak formulation for
Just the weak formulation. Okay.
Yeah,
Just
yeah. Okay. All right. So All right, ergodicity, stochastic two-scale convergence. What was philosophically, what were the ingredients of what we did? We had some type of convergence for the coefficients, the diffusion tensor, the chemotaxis coefficient, and we embedded that into the weak convergence definition so that we can pass the test function, so we can deal with the product of two sequences that were convergent, weakly convergent, right? But now the problem is that what we have now, we have that these functions over here of x, they're going to also be functions of a probability space, measurable functions over the probability space. So if you want to visualize that, instead of having this periodic configuration of disks, you could have these disks, the centers of which are dropped according to a Poisson random field. All right? And so the idea now is that in principle, as epsilon goes to 0, this doesn't have to converge to anything. All right, so we will have to have some sort of a law of large numbers, some sort of an ergodic theorem to ensure convergence here so that we can embed that convergence in the definition. Okay. All right. So, so I'm going to do something a little bit technical, but here is we need two conditions on these random fields. Right? By random field, I will just basically mean functions of your geometric random variable x, the Euclidean random variable, and functions which are jointly measurable on x with respect to the Lebesgue measure and omega with respect to the probability measure. Okay, that's what the random field is. But we would like to have some conditions of this random field. The first condition that I'm going to assume is that these random fields are kind of statistically homogeneous, which means that if you think of these disks that I drop, then the probability of having 3 disks on this part of the space is going to be the same as the probability of having 3 disks on that part of the space. So you can think of this operator semigroup over here as translations for the moment, just to help you visualize. All right. So this is just to express this homogeneity of the random fields. So basically, we're going to have this operator semigroup from the probability space to the probability space. I'm assuming that both Tx and T minus x are measurable. This is an operator semigroup. It satisfies the semigroup property. T of 0 is the identity. And we're going to assume this is the homogeneity, that the probability, the underlying probability measure, the Poisson spatial process for dropping the disks, as an example, if you want to have this in mind, okay, is invariant under these actions of these operators, all right? Invariant under translations, if you want to think about translations, all right? So the probability of T minus 1 xf is equal to Pf for every f measurable, right? Okay, in omega. Now, this just happens because you have assumed that both T and T minus 1 are measurable. This can happen that also the probability of Txf is equal to Pf, all right? And some technical conditions, joint measurability and so forth, all right? And then the random fields are going to be defined in the following way, all right? D omega x, maybe I should have written this dx comma omega, right? But I have this as a parameter here, is going to be basically some function over your probability, some random variable over your probability space, all right? Applied to tx of omega. Now, if you think about that for 5 seconds, basically this tells you that the probability of this taking certain values is the same on different parts of your space. This means stationarity. So that's the first assumption that I'm going to have. Now, does stationarity imply some limit as epsilon goes to 0? No. All right, we need one more condition. Here's the second condition, which is ergodicity. All right, so ergodicity, it will help you if you think about this for a moment, just for a moment, if x is in R, if you think of this as a stochastic process. So let's go through that. A measurable function, a random variable on omega, is said to be invariant for a dynamical, I will be calling these dynamical systems, although they're parameterized by vectors instead of time, but that's very common in probability theory. All right, these operators, semigroups, they call them sometimes special dynamical systems. All right, so f is going to be invariant if over every trajectory, all right, of this dynamical system, f is constant. And so an operator semigroup, these translations, for example, is going to be ergodic if every measurable function which is invariant, all right, if every measurable function f which is invariant for this dynamical system is equal to a constant. Let's see what this means. Imagine that this is a stochastic process. Imagine that you have R squared, and the left, you have a function that takes, imagine what happens when this condition is violated. This is a mixing condition. Imagine if the function f takes the value -1 in the negative part of the plane when x is negative, and takes the value +1 if x is positive. All right. So imagine a dynamical system that stays on the left part, all right? And it satisfies this property, all right? It satisfies the property that basically, because it stays on the left part of the plane, that basically the function is constant over trajectories. But that doesn't imply that the function is constant, which means that the dynamical system doesn't explore the whole space. There are parts of the space that it is missing. It's not mixing, all right? So that's a mixing condition. That's an ergodicity condition, all right? And under these two conditions, we can derive a limit, which is basically a generalization of Birkhoff's ergodic theorem for random fields. All right. So one more thing, we have these random variables over here, all right, with this Tx of omega. They have an image measure, right? You can take the measure in the probability space and you talk about the image measure. And this image measure is random, right? Because it depends on this omega. So there is this notion, stationarity can be expressed also in terms of random measures. What is a random measure? A random measure is a measure, all right, which is parameterized by elements of the probability space. All right, so here's the definition. So you can talk about the probability of having a specific measure, all right, because this is what is happening with the image measures of these random variables over here, all right? And the random measure is going to be stationary if whenever you convolute it with a test function, whenever you test it with a test function which is shifted, it is the same as testing it with a test function evaluated at y, and you shift the measure. Now, you don't shift the measure, you shift the measure if this is a translation, but you apply to the measure, which is parameterized by the action of the operator on omega. So think in terms of translations. All right. So under these conditions, right, I went through that very quickly, but this is kind of, let's say, standard material in the book by Bremen, for example, right, Leo Bremen. You have an ergodic theorem, which tells you, I have phrased this here in the one-dimensional setting, it tells you that if you have this operator semigroup, think of this as translations. Here I have one dimension, x is in R. If this is ergodic, the way we defined it, all right, and assume that the stationary random measure has finite intensity, this means something. I'm not gonna go into the details. All right, then you have the following result about averages. If you take the average over a trajectory, so if you initialize this at omega, all right, and you take the integral, you initialize with a set A, and now you expand, you inflate that set. And so if I was in Rn here, I should have t to the n times the value of A. But I'm in one dimension, I have t times the value of A. All right, with respect to the corresponding measure that exists in omega. So I take, let's say, I would like to say a temporal average, but here I'm not parameterizing with time, I'm parameterizing with space. All right, this is going to be equal to a spatial average. All right, with respect to something called the Palm measure, which is given here. All right, now notice that this measure, the Palm measure, if all of these mu omegas are the Lebesgue measure, which is invariant under translations, then what you end up with here is basically mu of A is P of A. So this collapses to the Birkhoff ergodic theorem from ergodicity, that you have seen probably in probability theory, right? That generalizes Birkhoff's ergodic theorem in situations that involve random fields. Okay, all right, so all of this is a bunch of definitions. None of these things is my work, right? This is just sets the scene for the work that Maria and I did. All right, so this is the background that we are gonna use. All right, so this is a result. At some point, late 90s, early 20s, there was this work by Aller, and a bunch of Russians and Ukrainians thought, okay, we can generalize this to scale convergence by Aller by using this definition of this result of ergodic convergence for random fields. All right. Mainly, the main driving force here was Piatnitsky. All right. So I'm going to set here mu omega of x. I'm going to have a fixed domain here. All right. So I'm going to set mu omega of x to be mu omega of x over epsilon. I multiply by epsilon, I scale, so I have this guy over here essentially. All right. And so here is the definition of two-scale convergence in the stochastic setting. All right. So we have a geometric domain as before. We have an ergodic dynamical system. All right. Suppose that Tx of omega tilde is a typical trajectory. What does this mean? This holds almost surely. So we want to pick a trajectory for which this actually holds. We don't want to pick some omega which is in a set of measure 0 for which this fails. Okay. All right. So suppose that you have a typical trajectory. We say that some sequence V epsilon, all right, will converge stochastically to scale. Okay. to some V. All right, so now we're mimicking the two-scale convergence parallel. We're saying there are a lot of technicalities here, but we're saying that, look, we're going to test this with functions, test functions that have a periodic component. And you don't have to decompose it multiplicatively, as I did here. You can. All right, so we have basically phi of tx, comma, x over epsilon, right, in Allen's definition. But here we're going to have t of x over epsilon omega. All right, so we're going to have basically the stationary action, okay, instead of the periodic component, okay? All right, and so we say that the epsilon two-scale convergence, these are the two scales, right, x and x over epsilon, if at the limit we're going to get, you know, an average over the probability space, in the two-scale convergence for periodic functions, we will take the average over the period, but now have the average over the probability space with respect to the power measure. We embed the ergodic theorem into the definition, okay? All right, why is this useful? A lot of details here. You have to assume some sort of a boundedness asymptotically. You know, this is not like, you know, this well-known, if you have weak convergence, it's not like you have weak convergence and you have to be bounded. You have to assume some boundedness, but this comes with compactness results, all right, that we need, all right, for stochastic homogenization. The first one, all right, these are exactly analogous to what we had for the periodic. All right, we're mimicking what we had in the periodic. If you have a sequence which is bounded in H1, okay, this is the geometric domain over here, okay, then we get similar results as before, okay. Now notice that basically, sorry, these are the assumptions, right? So you have that the derivative is bounded and in L2 and the function is bounded in L2. We get similar results as before. Before here, we would have the derivative with respect to the periodic component of V, right? But now here we assume that V1 is in this time-dependent Lebesgue space, not time-dependent, spatial-dependent, where basically you take any x in Q, give you a potential function in L2 over the probability space. So I have to define what this is, right? I'm talking about the gradient over the probability space, okay? But that would be the completely analogous result for the periodic convergence. And the same if your gradient is not bounded, but you have a slight generalization where epsilon times the gradient is bounded. And again, here you get some sort of a stochastic derivative with respect to omega. What is this? I mean, you can define this space H1 of omega with respect to the power measure by using this operator semi-group. If this is translation, that's exactly what the derivative would be, right? So we define the derivative of u. U is a function over the probability space. The only assumption here is that the probability space is a metric space, so you can define C of omega. All right, continuous functions over the probability space. Once you have this, you can define C1 of omega through the operator semi-group. You translate this by H, you let H go to 0, and you have this. And then you can define H1 by closure properties, all right? Okay, so you have sequences UK, you assume that you're going to have a sequence UK in C1 such that UK converges in U in L2, and the derivative of UK converges to the derivative of omega of U in L2. Again, the derivative is defined this way. All right, so you can define the H1 over the probability space through this action of this operator semigroup, right? And if this is translation, all the better. These kind of results in standard, you know, ends up with standard, you know, notions that you have. And you can do these decompositions to divergence-free, solenoidal, and potential functions in L2, all right? The closure, all right, in L2 of gradients, now gradients with respect, derivatives with respect, the stochastic derivatives, right, with respect to omega, and the orthogonal direction of that, the orthogonal complement of that, okay? Which is going to be the solenoid field, divergence-free field. All right, good. All this is background material. Let's go back to our problem. Look, we want to do stochastic homogenization. Here is our problem. We need two things, all right? We have statistically homogeneous stationary random fields. T of x is supposed to be ergodic, all right? So first of all, there is in the literature, there is a lot of results, there are a lot of results in the literature about the solvability of the system, all right? And when the solutions exist globally in time, when they kind of blow up. Everything I'm going to do here is in 1D, but in the paper we have also done it for 2D, 3D. You just have to incorporate the conditions on the conditions on the magnitude of the initial data so that you have a global in time solution. All right. So in 1D, what we did with Maria, we reproved existence and uniqueness for these guys, all right? And let me take you a little bit through that. But we did it, okay, there are some assumptions, I'm gonna come back to these assumptions. Notice that for the cells, there's just the assumptions that you would expect, some sort of a, basically here I'm in 1D, but we are bounded away from zero, some sort of a uniform electricity or something, right? We have some derivative assumptions for the chemoattractant. Initial conditions, notice that we have bumped up the regularity for V naught, the initial condition for V naught. But the idea here is that what we did with Maria is that we proved a priori estimates where C over here, the constants for these a priori estimates, is independent of epsilon, because this is needed for us. And this didn't exist in any of the existing, wasn't there in any of the existing proofs. So here is our setup, and I don't have the initial condition here. All right, so first of all, look that we're looking for solutions in H1. All right, so I'm going to have Neumann boundary conditions, which is kind of reflected a little bit on the setup here. All right, I'm not looking for H1 0. Notice that I'm bumping up the regularity for V epsilon. This is for the proof to actually work. Right, I'm going to tell you about that. We're going to use the Sauter fixed point theorem. And so we need to bump up the regularity for V epsilon. All right, all right. And we want these things to hold almost surely in omega, because again, we have the dependence on omega. All right, and of course, we want the initial conditions to hold, which I haven't written here. All right, with the regularity, the initial conditions have the regularity that I had in the previous slide. All right, so I'm not going to go through the specific a priori estimates, but I want to give you an idea of how basically we prove existence and uniqueness for that, how we go about it. All right, so here I have written it, it's a fixed point argument, so here I have written it as an iteration, but don't think of this as an iteration. We do this standard trick where we say, all right, so here are the equations. All right, of course, here we have this nonlinearity. So instead of dealing with the nonlinearity, first define an operator, all right, K, that will take as input some V hat. All right, and I hope I haven't written V hat here because I have it as element of the previous iteration. But that operator takes as input an element of V hat, an element V hat, which is in this space over here. And I'm going to tell you why I have bumped up this regularity over here. All right, and returns, it solves basically this linear system. All right, and it returns some V. All right, in this space over here. Okay, H1 intersection L infinity, time dependent backspace. Okay, L infinity from 0 to H2 of Q. All right. All right. Now, the important thing is that you can use similar a priori estimates as the ones that I had in the previous slide, in the previous slide, to actually, because this is a linear system now, because we have V hat, to prove the solvability of the linear system. That's a linear system now. All right, so you use Galerkin's method, weak convergence methods, projections to finite dimensional space, weak convergence method, weak compactness methods, and you get this kind of regularity. Now I want to use, so now if I find a fixed point argument, so this V hat over here, if I find a V for which V is equal to K of V, I'm done. I'm gonna get the solution for U because this is a byproduct, and I'm gonna get a V. Right, so I'm going to use Sauter's fixed point theorem. Right now, a version of Sauter's fixed point theorem is that you have a continuous operator from a compact convex subset of a Banach space back to that compact convex subset. It has to have a fixed point. Now here we're in trouble, of course, because these spaces are convex, but they're not compact. All right, here's where we need to use compact abelians, and that's why I had to bump up the regularity over here. All right. So the idea here is that you say, all right, here's what is going to happen. All right. So I'm here in this L infinity with respect to time. So obviously 0t is a compact space. So obviously I'm in L4. All right. Now I'm going to lose a derivative here in H2, and I'm going to do the compact abelian in W14. All right. For these two spaces. And then the Aubin-Lyon lemma will give me the compact abelian for the time-dependent isomorphic spaces. All right, and now, all right, I have a compact abelian, but I still don't have a compact space. But here is where these a priori estimates are of use, because I have the a priori estimates. So I'm in a bounded, I'm going to focus now on a bounded set, and through the compact abelian, that bounded set is going to be pre-compact. So I take the closure of that pre-compact, I have a compact set, and that's where I apply that operator. It is convex. all right, because you have intersections of convex sets, it's compact. This is the thing with the Sauter fixed point theorem. You cannot go about it with weak compactness. You need compactness. So you need to employ compact. Sorry, that was a question.
The compact embeddings that you need for the solid compact embeddings sometimes depend on the dimension. So this is 1D only.
This is one thing, and that's very good.
And that's
Yeah.
in 2D, it probably is some things are.
It's something slightly different. So if you see the paper also in 2D, I should say, and that's something, it's a good question, Manuel also asked me that. C here doesn't depend on epsilon, but depends on tau, this tau over here. All right, and the thing is that in 2 dimensions and 3 dimensions, you don't have global solutions in time. So you have to set extra conditions so that you know that you don't blow up, and the compact embeddings will be slightly different. All right, so it's slightly, the level of difficulty goes up, right? But here I just show the easiest part of it. And of course, it's not easy, right? All these a priori estimates were a pain, but that's, I'm showing you the high level kind of argument. All right, so we have a unique solution. You can prove uniqueness. All right, so let's go back to the thing that we want to prove. All right, so the problem, the stochastic gradient ascent with a microstructure has solutions. All right, now we want to investigate the question, do the solutions that depend on epsilon converge in some sense? All right, here you see I have some sort of a weak convergence in this time-dependent Lebesgue space, but the idea is that also from this you can derive strong convergence in L2 of the product space between how do you call it, a spatial space and time, the Cartesian product of space and time. You know, the thing is that we are gonna prove convergence to the solutions of this PD. Now this PD doesn't involve the microscale. All right, okay, and doesn't involve any stochasticity either. All right. So you see this D star and X star here, they depend on these quantities, and this U1 bar, I guess, and U1 theta or hat, I guess. Okay, they're given by these conditions. All right. The fact that this expression over here belongs to L2 solenoidal tells you basically that it satisfies an integral equation, right? So the integral times a gradient of a test function has to be equal to 0. All right. So, all right, how do we do that? Well, now that we have all this machinery, all right, with the stochastic two-scale convergence, we can mimic the two-scale convergence, the deterministic two-scale convergence a la Allaire, right? Okay, so first of all, you know, we have all these sorts of a priori estimates, so we can use these two-scale compactness results, and we know that, for example, U epsilon will converge to some U, two-scale, where U is in some space. All right, the derivative will converge to something that involves this U1, which is solenoidal, is the gradient with respect to the probability, the stochastic gradient. All right, so this is over here solenoidal, that's going to be important, okay. And then the derivative with respect to time of U epsilon also will converge to something, all right. All of this comes from the estimates. The estimates, if you remember, involve the time derivative as well, okay, here. All right, so also you have corresponding, I didn't want to have a very busy slide, but you have corresponding convergences, weak convergences for V. V doesn't depend, you know. All right, so you use all this stuff. The convergence, the stochastic two-scale convergence of U epsilon implies weak convergence of U epsilon. So, you know, two-scale convergence is a little bit above than the weak convergence. And by a compact embedding, you can also prove strong convergence of U epsilon. I have 5 minutes, okay, let's go very quickly. All right, so basically what you do then is that you go back to the equation that you are interested in. All right, this equation, you write it in weak form. All right, you write it in weak form and you use all these convergences, right? So here is the thing with respect to time. All right, you use as test function something of this form. All right, you see, this is not, you know, this is for every x and t, I have an ergodic, it's like with the periodic things, right? For every fixed x and t, I mean, the general case, right? I will have a periodic function. Okay, so now for every fixed x and t, I have something which is basically an ergodic test function. All right, okay, so basically here I have integrated, by parts once, you see, I have passed the divergence here to the derivatives over here. I'm assuming here that this t is translation in this case, so basically, you know, this derivative with respect to x here will become derivative with respect to omega. Okay, these things don't matter. I take the limit as epsilon goes to 0. All right, so this term over here will disappear, so I will have the inner product of phi with ut. I test the derivative with this guy over here, because I know that u epsilon of t converges to scale. All right, same situation here. I have the product of two convergent sequences in the two scale sense. No problem, because I can deal this with two scale convergence. It's not weak convergence. Here I have this non-linearity. I have a problem. But by compactness compact embedding, I know that u epsilon converges strongly, and this guy converges weakly, converges to scale and hence quickly. So everything passes to the limit, and I get this guy. As I pass to the limit, I get an extra integral. You see, I integrate here with respect to space and time. I get an extra integral and average with respect to the probability, because that was part of the definition. Okay. And now, okay, I will complete the talk. Basically, now you end up with this, and now we mimic what we did before, right? This doesn't involve, all right, it does not involve the microstructure, but it has this annoying U1. We want to get rid of this one. But we have all these test functions over here, all right? So basically, first, what I'm gonna do is that, where is it? Oh, I did it already, actually, in the previous slide. I did it here. I have this test function over here, or these test functions phi, phi1, phi2. First, I set phi to be equal to 0. Right, if I set phi is equal to 0, I'm getting this guy, which involves this one that involves omega. This is true for every phi1, so I can get rid of the integrals with respect to qt. So I'm gonna end up with this integral with respect to omega only, and only phi2 over here, almost surely. All right, and that will allow me to express u1, which remember is solenoidal. All right, sorry, u1 is not solenoidal. What am I saying? u1 is potential. It will allow me to express it as a linear combination of the gradient of u and u times the gradient of v that appears here. All right, so I'm gonna have something like that. All right, where now if I take this and I plug it up here, I can verify that u1, I can verify that specific expressions are orthogonal to a gradient, so they're gonna be solenoidal. These are the solenoidal conditions that I had in the limit, in the theory. All right, so then I take this, I plug it back to the original equation. All right, and now I set phi1 is equal to 0 with that expression that has gotten rid of u1, and I will get these coefficients. I will get these coefficients over here. Okay. All right. So that's how it works. All right. So is ergodicity needed? What we did with Maria, you can say, well, okay, what about if I don't have ergodicity? 1 minute, I'm gonna end. Right? What about if I don't have ergodicity? I have, random fields, omega, z, but what I do if they're in a compact domain, here I'm in the one dimension, I extend them periodically. So I can apply tools from periodic homogenization for convergence. But because I don't have ergodicity, you can get rid of the microstructure, but you cannot get rid of the stochasticity. So in this kind of situation, you do the periodic extension, you get a limit, you get a PD on the limit, but that PD has stochastic coefficients, all right, because you don't have ergodicity, all right? So what we showed with Maria is that, okay, if you take that, remember the domain was 0 rho, right? If you take that rho, go to infinity, if you take these coefficients, homogenized coefficients that don't depend on epsilon, and you take rho, go to infinity, these depend on rho, right? And you obtain this through this periodization procedure, and then you let rho go to infinity, which means that you cannot do the periodic extension anymore. You recover the coefficients that you get from ergodicity. Right, so this is good for computational reasons. This is something that it's a very standard. This is something that people do. It's not always people are not always able to obtain results like that in stochastic homogenization. But when they do, is a desirable result. All right. Okay.
Questions?
Remember, I'm trying to remind myself some of the technicalities here because I have some new results. So feel free, any technical question that you may have, feel free to, yeah.
Can we extend this homogenization to non-periodicity, like, for example, in the Poisson equation, changing the dx divided by epsilon to a matrix that converges weakly in L2 or in H-1, for example?
Well, dx over epsilon converges weakly, depends how, okay, what regularity you assume for d of x. But if this periodic, d of x over epsilon will converge weakly in L2 to the average of
Yes.
the period.
Yes, but it wasn't a periodic matrix, but it was like an d epsilon matrix, which wasn't periodic.
Yeah, so what I had was a generalized version of that, which is kind of appears frequently. I had something like d of xy, all right, where this belonged to some space. For a moment, let's assume that is in C infinity. You know, suppose that x is in, I don't know, on the real line, right, or something on Q. Q, semicolon, I mean, these are the kind of spaces where C infinity periodic over some period y. Now, what this tells you is that for every fixed x, I have a periodic function of y. So this allows, in 1D, it allows functions of the form, I don't know, x plus sines of y. And then I replace here the scale, I put x over epsilon, which is not a periodic function, but it allows you things like, you know, things like functions that have a periodic component, let's call it. All right, which was slightly. And that will also weakly converge to something that depends on x and it has the average of, so for example, here that will weakly converge to x times the average of the sine over its period. All right, so that was, it doesn't have to be periodic, but you know, usually you have a periodic component, periodic homogenization. What we had was basically randomness, and I didn't explain it well because I didn't have enough time, but the thing to visualize it is always, for example, these disks. These periodic coefficients, by the way, I should say, they are, this is very applied in the sense that you can, you don't know in a specific tissue where every protein is, but you have statistics of the locations of the proteins. So you can impose certain statistical properties of these on these random fields. All right. So the idea here is that you lose, once you do that, if you don't have ergodicity, you lose that law of large numbers, let me call it, the ergodic theory, right? So you lose something like what you have here in the periodic setting. That's why I had to go through all this machinery with the parameters, etc. I don't know if I'm answering the question.
It's really clear for me, but thank you.
Right.
I don't have a technical question. I have more of a philosophical question.
Okay, yeah.
What is the point? The point is that you can zoom out basically, right, and solve the things when you're zoomed out. I think that's the ultimate point. Is this ultimately?
Yeah, this is.
I mean, how can we use it as a tool? Like, okay, so you homogenize now. What do I need to solve?
Right. This is desirable for two reasons. So these results have been used. There are two reasons. The first reason, the first quick answer is that look, this is useful in terms of numerics. This is not numerical analysis, but the idea here is that, you know, if you have a separation of scales, of course you can refine the grid and you can do adaptive stuff and, you know, you can do whatever you want. But if you know that you have a separation of scales, for example, in periodic homogenization, right, then you know that you can approximate the solution with a microscale by the limiting equation, which is easy to solve numerically because it doesn't have a microscale. All right, so that's how this traditionally has been used. Historically, that was the reason why that was invented in situations with crystals and stuff like that and material properties and stuff like that. Okay, even nowadays, I think that's a little bit of my beef with the numerical analysis community is that they think that all these things work only for periodic homogenization, but that's not the case. All right. So it works even for random heterogeneous materials if you assume certain assumptions for the randomness.
I didn't complain.
No, not you. Right, but you know, I have seen. But another thing that this is very useful for is exotic materials. All right, because you can think this kind of Poisson relations, this thing that we were discussing the other time, like in elasticity, that you think you have a normal material, you stretch it and kind of squeezes, but there are materials that you stretch them and kind of elongate in this direction. You can design these materials with a specific microstructure. But in order to do that, you have to know the macroscopic equation. It's not easy to derive this result with a microstructure, even analytically, right? So these kind of asymptotic results are used for designing exotic materials, right? For us, the idea was like, if somebody gives me statistical properties of a tissue, and that's more generic in some sense because it's stochastic gradient ascent, like that you can use it for optimization, for whatever you want. I have students here now that work with stochastic differential equations on stochastic gradient ascent, and you know, we modify the parameters so that we can accelerate the algorithm. But the idea there is that For us, we wanted to have a model which is more reliable if you have knowledge of the statistics of the province and tissue, rather than the things that everybody is using in these kind of situations and they fit to data in biophysics, where they have some homogeneous diffusion coefficient like ink and water, which is not how cells move in tissue, right? That is the, yeah, this is the motivation. And the other thing is that, basically, I met Maria in a conference and I was very knowledgeable of ergodic theory at that point, and she was very knowledgeable of periodic homogenization, and we thought, okay, we're going to teach each other, and it was good mathematics, right? That was the other. Yeah, okay. Yeah.
I wonder, do you get some, can you get some estimate of the distance between the homogenized solution?
Yeah, so that's an excellent question. These are usually called, in the periodic settings, they're called collector results, because you get this kind of weak convergence results. And then the idea is that, can I get, for example, some sort of in that two-scale convergence, it was like this was our expansion. Like, we didn't have any expansion or anything. You have this two-scale convergence, but the compactness results, etc., were behaving like that, right? And the question is, can I have a strong convergence and derive the rate of convergence? Okay, so of course, for the Poisson problem, this has been done. For prototypical problems, these are called collector results. Okay, we haven't been able to do that for chemotaxis. In one dimension, we kind of were able to do it, but in 2 dimensions, because you have all these complications, it is in the everything I did here, we have it for 2 and 3 dimensions. But there are things that are very difficult. They're more difficult, let's say, because you really have to control for the blow-ups in finite time. Right. And so we didn't have any collector results or anything. But for the 1D, yes. But yes and no, because we got the strong convergence, but we didn't get the rate of convergence. All right. So yeah, the rates of convergence are always difficult. Yeah.
You don't get an estimate of U1. In any norm, you can project that.
No, U1, in some sense, but you don't know the L2 norm of U epsilon minus U1 minus epsilon U1. That's what you want, right? You want the distance. As epsilon goes to 0, you want a strong convergence result, and you want the distance of this guy from this guy, right? And you want the rate of convergence, like how fast.
Well, that would be the idea, but at least you could have an estimate of U epsilon minus U naught.
You have to go back and look, but these are also.
Because you have this expansion, of course, you can compute
Yeah.
that, then you get the error bounds.
Yeah. Keep in mind that this is something that you want, the distance of U epsilon from U naught. Keep in mind the expansion, the clever thing of these methods is that you circumvent the expansion, right? So you get the results that are consistent with the expansion, but you don't know if the solution will have an expansion of that sort, etc. Right? So that's. But what you are saying is valid. That you would like, these are the so-called collector results. You would like to have an estimate of the L2 norm or whatever norm, right?
Yeah.
Of U epsilon minus U naught, for example.
Yeah.
We got estimates because of how two-scale convergence works. Estimates between for the 1D, the norm of U epsilon minus U naught minus epsilon. Yeah.
Very ignorant question. But
No. None of your questions are ignorant. I'm always afraid when you ask me this stuff. So, all right.
So in homogenization, you said you could typically use separately, maybe a div curl lemma, or you can use compensated compactness, or you can use a 2-scale, and they're all separate approaches, right?
Right.
Is there any kind of inclusion among them?
Yeah. So there are these things that go back to Tartan. Depends what kind of equation you have. Here we had some sort of a non-linearity, but it was like excuse me. There are people like, what's his name? That good guy, Chicago. They do homogenization of Hamilton-Jacobi and stuff like that, which is fully non-linear. These techniques don't work there, because here we assume some sort of a linearity, right? You have to have some notion of weak solution through viscosity solutions, etc., right? So there are things called, which are for fully non-linear PDEs, like, and I'm not knowledgeable of these things, but I know they exist. I'm talking now about things that I don't know. There's something called H convergence for homogenization, right? H homogenization, which is for fully non-linear PDEs, right? And it takes advantage of viscosity solutions, and so there are different techniques. This kind of technique with the two-scale convergence parallel would work for a semi-linear PD, something like that. Like you still would like to use this machinery with test functions integrate by parts, which wouldn't work in a fully nonlinear Hamilton-Jacobi. Then you have a completely different notion of weak solution as a viscosity solution. So all of these things have to be adapted to the kind of PD that you're using. Now, to your question whether there is some sort of inclusion, whether some method, the difficult lemma is very specific. It says I have two weakly convergent sequences, U and V, if the divergences of U converge, right? And if the curl is 0. So it's very specific, it's for fluid mechanics, it's, this is, to me, this is more flexible, more adaptable. Now, if you start going to fully nonlinear stuff, the technology changes dramatically, right? So our objective here was basically to take something which is well known, it works for periodic homogenization, and then to kind of extend it to a stochastic setting. Then we realized that somebody else had done it, right? This stochastic two-scale convergence. But then still, in order for that to work, we needed to have estimates that were not derived, which were independent of epsilon, and stuff like that. So we had to put the work in, right, to do some stuff. It wasn't trivial. It took us, well, we were on and off because we were in different locations. But with Maria, I think it took us, it's fair to say it took us 2 years. And if you see the papers, 2 years. It wasn't 2 years of continuous work, right? 1 month we would work on that, then. But this finished when I got a sabbatical at ETH, and Maria got a sabbatical somewhere else, I don't remember. And we had a lot of time to actually, not teach it.
So there could be, for example, like a stochastic difficult lemma that you could use specifically in fluid dynamics. Maybe think about modeling turbulence in some sense.
Yeah. It depends how you want to set it. If you want to set it almost surely, I'm pretty sure that it can be done easily. But then it depends what kind of here we got around because the tools that we used were mostly PD tools, and our convergence was almost surely. But that wouldn't always be the best thing to do. So you can have different convergences with respect to the total variation distance, with respect to the Wasserstein distance, which is weak star convergence, so it depends what you want to employ, things have to be modified. Here, essentially, we had convergences that you get in PDEs, kind of weak convergence, weak type convergence, and everything was holding almost surely, right? So, yeah. Yeah.
Thanks.
All right.
All right, let's think.
Okay.